So once again, thank you everybody for signing up and joining us this afternoon for our webinar today. This is our fall 2025 webinar series. Today we've got Eric Cowan, who's going to be presenting a talk on the exciting topic of LNAPLs and risk assessments. So we'll run through a few logistics first. So I have a bit of an upfront introduction for you. I'll turn it over to Eric for the main portion of the webinar, and then we'll have ample time at the end for a Q&A period that we can go through. I would ask that you can either use the chat feature or the Q&A box on the webinar to input your questions as we go, and we'll hold them all until the end. I'll present them to Eric, and he can respond to them at that point, okay? For those of you who are not aware, VEI Contracting, we were formerly known as Vertex Environmental up until last year. Now we are VEI Contracting, like I said. We've been around for over 20 years, specialized environmental remediation contracting firm originally, but now we're into construction dewatering and general contracting. And we do work coast to coast across Canada. I'm the host today, Kevin French. I'm the Vice President of VEI, an environmental engineer, and I work closely with Eric on many of these remediation projects. I mentioned VEI does work coast to coast. Our main office is located in Kitchener, Ontario, but we also now have staff in New Brunswick on the East Coast and in Victoria, BC on the West Coast. So we're even better suited now to deal with your environmental site needs wherever they may be in Canada. And this is just a quick shot of the range of services that we offer. Today, we're going to be talking about both some characterization work up here, this high-res and RDC feature, as well as in situ remediation. We had a previous webinar a month ago on dewatering and hydraulic profiling tool. If you missed that, again, it will be posted on our website shortly. This is the one we're doing today. And then we have two more upcoming in November and December. One is on PFAS treatment, full-scale case study, and the other one is on metal leachate acid rock drainage. So be sure to sign up for those ones as well. And now I will turn it over to Eric, who will start the main portion of the webinar today.
Awesome. Thank you, Kevin. Okay, so just a quick overview. I'm going to be talking about LNAPL and RAs and some of the nuances between different provinces before we get into some of the technologies, specifically with LNAPL characterization to help with developing a CSM for a site. And then hopefully with a well-characterized site, you can then move on to some destruction or immobilization, treatment techniques to help with your LNAPL problem. And we'll be going into what that looks like with injections specifically. And then I'll close out with a case study with a very interesting site that we recently completed. And so I won't go through the Vertex thing, but for myself, I am a senior project manager with VEI. I've been over here for over 10 years. And I work specifically in the remediation division with Kevin, primarily focused on injection techniques for in situ remediation. So let's jump into it. So what are some of the details with LNAPL and risk assessments across provinces? So I'll just go into some they're pretty similar, but there are some nuances between some of the key provinces. And so with Alberta, they do specify active remediation or removal to the extent practicable, right, for mobile LNAPL. And then for non-mobile, it's more of a control. And so they really want to see that it's stable or decreasing in the source control. And then this is pretty common across all jurisdictions, but they likely want to see some sort of risk management with exposure control, so vapor or what have you. And then with British Columbia and BC, it's a little bit more detailed, and they do specify a monitoring program for 1 year to determine that it's stable or not mobile. And then they actually have a classification of high risk site for properties with LNAPL over 2 millimeters, so sheen or higher basically. And then that can have some issues with your classification of the property. if you have that. And again, you must assess the vapor intrusion considerations in BC. So what do we have here in Ontario where VEI is centralized? We have a kind of a similar process, but there is some permission for LNAPL in Bedrock, but it's not preferred, of course. But in an overburden, it's very rare that they would allow an RA with overburden LNAPL impacts, and probably impossible. And so again, they have this term to remove LNAPL to the extent practicable, including films, sheen, and 50% solubility. So I'll get to that in a second, but that term extent practicable, I want to highlight because it's in the title, but it doesn't mean the cost, right? It's more about the technological availability to do this, right? It's not an excuse to say, oh, it's too costly to do this. Rather, it's you have to have an excuse of, well, it's just impossible technologically to do this. And then to the point of the 50% solubility, this is something interesting in Ontario, is that you don't actually need to detect LNAPL, but if your groundwater concentrations are considered above 50% solubility, that actually could highlight the potential for a product to be generated, right? And so that could be flagged under the RA assessment. And then again, like the other jurisdictions, the vapor intrusion considerations must be addressed or assessed. But what about Quebec? It's actually RAs aren't allowed for PhDs in general, so it's kind of a no-go there from the get-go. So the whole point of this talk, really the objectives, is to look into a way to effectively destroy or mobilize LNAPL for an easier RA approval, right? And so we want to see an assist with reducing offsite risk and the need for barrier walls, and we're addressing groundwater, surface water migration pathways with these techniques. We're reducing the vapor concerns that may come with it, and we can actually shorten length of monitoring programs when we're doing this. And so we can jump right into what are some of the technologies that can assist with this. And like I mentioned at the top, the conceptual site model, really understanding your LNAPL plume is kind of the first step. And something that can help with this is a technology called laser-induced fluorescence. And so this is a tool specifically used to detect free-phase PHCs in situ with a direct push tool that uses UV light to excite the polyaromatic hydrocarbons, PAHs, within the free-phase PHCs. And that actually creates a fluorescent effect. And then within this probe that you can see on the left here, that collects that fluorescence response, and we can actually detect in real time the free-phase PHCs, and we can actually fingerprint what type they are as we advance this direct push tooling. Get into more detail in a second of what that looks like in a report. But the idea here is we can add on to an existing standard environmental investigation with boreholes and monitoring wells, an additional semi-quantitative response to say, hey, we're actually seeing in real time these plumes and where they are, and characterize it in a much faster way. So you can do 10 to 12 points a day and get data in real time. And we also add a EC electrical conductivity sensor on this as well, and we can classify the soil types as we do it. So what does this look like? So here's an example of what crude oil and diesel just look like with the naked eye. And so you can see crude oil quite easily, right? And you can see that with just regular light. And diesel is invisible. And so when you flash UV light on this on these jars in this example, you can see the crude oil has a fluorescent effect and as well, but the diesel, you can actually show that it's quite hidden without this UV light. And so you can maybe see a little bit with your naked eye, but you can see above that, there's these globules of diesel that were hidden unless you expose it to the UV light. And so that is, again, to those aromatic molecules, the PAHs, they absorb that UV light and then fluoresce a response that we collect with the LIF. And so what does this look like in a log? And so this is what the field technician will be seeing on their laptop in the field as they're advancing the probe. And so we have two examples here of different fingerprints of fuels that were found in the ground. And so on the left is an example of a diesel spill that was identified with LIF. And you can see the green coloration in the response, which is along the x-axis. And so Depth is on the y-axis as you're advancing down. And each of these, I can highlight with my mouse here, callouts is called a fingerprint. And we have a different term for the lighter or heavier fuels are either blue shifted, which means there's more of a lighter pHs like naphthalene, or they're red shifted, and that's something heavier like diesel or heating fuel or crude oil. And so that creates these fingerprint callouts, and we can actually identify and speciate the type of pHs in the ground. And so you see diesel has a green, like have a green coloration of the response, and that's the average of these wavelength peaks on the left. It's a little bit more red shifted, whereas something like kerosene jet fuel is very much so blue shifted with lighter pHs, smaller pHs being dominant. So it's a great tool to identify the actual type of pHs, not just where they are. And so we can also call out this into a 3D visualization. And so this really helps with our CSM to understand the plume of LNAPL site. And this is just an example of that. But we can move on to destruction techniques. So what happens when we have done these characterization tools, we've used these tools, we have a good understanding of what the plume structure is, and we want to now address it with treatment. And so the first technology I'm going to jump into is trap and treat BOSS 200 plus. And so this is a combination of activated carbon, which is the trap portion of the amendment, with different terminal electron acceptors and nutrients and microbes as the treatment portion of the carbon trap and treat. And so what this means is that activated carbon, like you would find in a Brita filter or that actively used in water treatment systems, is very porous and can trap or absorb PHCs within the micro, macro, and mesopore, small to large pores within the structure of the carbon. And so when we include terminal electron acceptors and different microbes, and these exist naturally as well into the subsurface, but we add them along with BOSS 200, you actually create biofilms and degradation sites within the pore structure of the carbon. And this is very powerful because it not only you can remove these PHC mass from the subsurface and from the dissolve phase, and we'll talk about LNAPL as well, but you're actually destroying it within the carbon structure and freeing up more space for additional trapping when the eventual destruction happens of the PHCs within the pore space. It actually has a regenerative effect, and so you're trapping and treating, degrading, and then once that's gone, they're kicked. The end products are kicked out, and that opens up more pore space for additional treatment. And so what does that mean for BOSS 200 plus? And so this is actually just a kind of enhanced version of the base product BOSS 200, which is activated carbon and those TAAs and microbes I mentioned. But it increases, we add some additional nutrients and TAAs and some other specially designed microbes to basically enhance the degradation effect to increase that PHC limit, so we can overcome some of that soil mass limitations if there are at LNAPL sites. So essentially, we can treat more, we can degrade more PHCs per gram of carbon, and allow for sites with heavy soil mass or LNAPL, or even recalcitrant compounds within heavier pHs to be treated within this BOSS 200 carbon structure. And so BOSS 200 Plus has been around for almost 8 years, specifically in the US, but in Canada, it's only been a couple of years. So 2023 was its first use. And again, its main application is source area LNAPL remediation, or you can use it in PRB applications as well, if your contaminant flux is quite high and you need a little bit more within that PRB. And so you can place this via injection, which I'll talk about, or backfilling and soil mixing as well. And so, yeah, the key thing here I want to highlight is it overcomes the contaminant mass limitations of PHCs in soil. And so you can address some of these heavier soil mass sites or LNAPL sites. And in doing so, because we're adding this carbon amendment that's very persistent, it actually prevents back diffusion and rebound, because that amendment is existing within the pore structure and works for years and years. And with that regeneration effect, you're able to keep that system going with trap and treat. And usually it's a single application, and again, it's a long-term solution. So this is a very cool figure image from the suppliers of trap and treat. It's a image of biofilm generation in the bubbles, you can see this microbial activity occurring on the actual carbon pore structure. And so what are the actual absorption limitations of standard activated carbon like you would have on, say a water treatment system? And studies have shown it's usually around 20 to 25% by weight. So this means that the saturation absorption capacities of PHCs is, if you were to have 1 kilogram of PHCs, you would need 5 times that of carbon to effectively absorb that mass. But with BOSS 200 plus, before we even get into the destruction technology, the carbon that they use within that trap and treat has actually been measured much higher. It's at almost 60% by weight. So you almost get more than double the absorption capacity of PHCs compared to just a standard granular activated carbon. And one of the key things we like to specify here, and RPI likes to show in some other studies I won't get into, but the actual adsorbed PHCs that enter the pore space of the carbon can get down to the micropore level, so very small spaces, and they're still bioavailable there. And there isn't an issue of it's only treating in the large pore spaces and maybe not everything, but they can show that it is bioavailable and it can be treated even down to the micropore level. Basically, the bugs can fit in there and it does work. And so when we get back to that regeneration topic, there's been studies that show it actually recovers a substantial amount of that absorption capacity. So your carbon traps PHCs, it treats them, it then removes the end products, and then actually can recover over 90% of that original absorption capacity following that first round of treatment. So that's very, very powerful. So what about LNAPL? Is there a limitation with activated carbon when we do have sites with high soil mass and LNAPL levels? So this gets into some of the kinetic data that we can discuss, where we can actually show that BOSS 200 plus with some of the things I just mentioned can actually degrade up to 1 kilogram of PHC mass for every kilogram of AC per year. And so this really is powerful in the sense that we don't need that 5x of standard carbon to address the 1 kilogram, the 5 kilograms of carbon to 1 kilogram of PHCs in standard carbon, but you can actually have a much lesser mass of BOSS 200 plus to address basically that 1-to-1 PHCs to activated carbon. And then that regeneration effect, again, even when it's saturated with LNAPL, is a viable process. That regeneration can occur and you can free up more space. And so overall, it's a coal-based activated carbon amendment, and it has the necessary properties, like I just mentioned, with that degradation mechanism to address, realistically, these LNAPL impacted sites. So moving on to another technology, in the case study I'll go into the end is going to be about trap and treat, but I wanted to mention immobilization first. This is specific to sites where there is LNAPL, it's mobile and it's causing an issue, potentially to nearby receptors. And perhaps there's the objective isn't necessarily to treat and destroy everything, but you really just want to immobilize LNAPL so it's not a migration risk or a mobile risk. And so the concept here for this technology, it's called block and absorb. And it is essentially to bind that mobile LNAPL in high concentrations of PHCs in soil and groundwater and lower the formation permeability in general to then block that PHC mass in LNAPL from migrating. And it's quite simple, actually. It's just a mixture of Portland cement and activated carbon. And so these are quite readily available and inexpensive materials that can be quite powerful when they're combined. And so we had a pilot recently where there was pretty high levels of LNAPL and shallow groundwater. And I can show you some pictures here. We're doing a test pit. And you can see here this bucket's basically full of pure product, just hovering above the water table. And so the goal of this pilot was to show immobilizing this product with block and absorb. And so what we did is we opened up a pilot test pit. It was about like a 10 by 10 area. And we added granular activated carbon and we mixed it up. We then subsequently added Portland cement and did another round of soil mixing, and we let that cure for a few days. And here are the results. So you can see on the left here is a baler collecting a sample from the test well pre-soil mixing. And, it's heavily stained. There's, measurable thickness of product. And then here's the test well in the same location, post soil mixing, coming up with, zero visible product, if not looking extremely clean. And so what does that look like actually in the ground? So again, on the left is pre-soil mixing. You can see that really, visible sheen and layers of LNAPL. And then post mixing, we're actually not seeing any of that after our block and absorb was added. And you can still see, which is very key here, everything's still soil-like. We're not creating a mass block of cement in the ground. You're still able to dig this up and it's still geotechnically viable as soil. It's not just a big cement block, which is very important. So just to summarize, it's been proven effective at immobilizing LNAPL and sheens in soil in situ. And a key point that I mentioned, but if we were to add these things individually, you would have some solid effects of, blocking or absorbing by themselves. But when you combine them together, there's actually a greater effect and they work even better when combined. And again, like I mentioned, that soil is still soil-like. It's still malleable. You still be able to work with it. You're not creating a huge block into the ground. And we can inject this amendment for deeper soils or bedrock. We've done this, and if it's a site where maybe an excavation is not feasible, and we can do this without having to excavate. And overall, it reduces the formation permeability quite substantially. And this, with this, dissolved phase PHC concentrations in groundwater are reduced as well. So overall, no excavation, extraction, and waste generated, right? You're not digging and dumping, you're doing everything in situ. And this is considered sustainable approach compared to the alternative. So let's get into injection. Before this case study I'll jump into, I'll talk about how we actually inject some of the amendments, specifically with trap and treat. So here's kind of a profile view of what a typical injection system looks like. It has a injection trailer with mixing tanks and water tanks and injection pump. It then is connected to a direct push drill rig injection rod system. And then within that rod system, there's a pressure activated injection tip, which is very important. We can change that depending on the geology and what we're injecting. And we inject on a top-down system, meaning that we're injecting, shallow intervals first and working our way down. So the goal when you're injecting remedial amendments like this is you want uniform distribution and you want contact between the amendments and the contaminants, right? You don't want any gaps. And so what does this look like from a plan view? We stagger our injection points based off the radius of influence we expect. And so that's just how far the amendment is going out laterally from the injection tip. And we make sure that we're covering a grid-like pattern with no gaps in between them. And in the same line on the profile view vertically, we stagger our injection intervals between points to make sure that vertically it's covered and no gaps in that sense. Just a quick point here, something cool we've recently just implemented at VEI is our new environmental site modeling software. And so we do this for every injection program now. We can actually map out our injection plans in 3D, as you can see, and you see those injection discs at each point in each interval. And we can take all the site data we get from the property and upload it into the model with site plans, borehole logs. We can talk about high res data like lift data we can incorporate within the injection design. And then we have real-time updates from field staff while they're injecting. So you'll see the injection being completed by the interval, by the foot as it progresses. So it's very powerful, and we're implementing this now across every injection. And then we can get into bedrock. So, years ago, it seemed very difficult, if not impossible, to address just contamination in general in bedrock through in situ means, not let alone LNAPL. But we've had great success recent years with a new type of injection system using injection packers or straddle packers. And so it's kind of like an offshoot kind of taken from oil gas technology. It's basically a rod with two bladders on the top and bottom that can inflate to very high pressures, up to 1,000 psi. And what you do is you install a open borehole in the rock. And so you just basically have no well infrastructure, no screen or anything. It's just an open borehole. You install this injection packer to your target depths and then inject through the middle interval. And so you can do this to as far down as you need. It's a high pressure, high flow system. It's not fracking. We're not hitting into pressures that high, but we're just injecting amendment into the existing bedrock fractures by displacing groundwater and material within them. And then the next approach I'll say in a second is what happens if bedrock wells or boreholes are too fractured or aren't staying open, or even overburden geologies are too tight for direct push. We have another injection method called geotap. And so what this is it stands for geological targeted access point. And you can do this in bedrock and overburden, but essentially what it is you create a pre-drilled borehole and you backfill it with bentonite, and then you return with direct push to then inject through the bentonite into the formation, whether it be, again, overburden or bedrock. So this is very cool for sites where direct push is not possible, like flowing sands or tight tills, or bedrock where it's too fractured for the packer system. And we've done this probably now over 30 sites with great success. And a question I get a lot is, well, how do you know it's getting through the bentonite, right? You're trying to inject some sort of particulate amendment or otherwise through hole plug, essentially. And what we can show is, and what we argue and what we can prove with QA/QC boreholes is that when we use these high pressure injection tips, which is what this photo is showing, the high velocity of that pressure activated tip and the injectant itself actually slices through the bentonite into the formation. And we can prove these two ways. So first, we just don't see bentonite blowing up the hole like toothpaste. So that's a good start. We're not displacing anything within the borehole. But two, we at most sites we conduct QA/QC boreholes nearby the injection points and collect soil samples to confirm visual, detections of the amendment within the injection areas. And we've seen that at all of our sites that we've done that, which is great. Okay, so now that I've highlighted those different technologies, I can talk about a case study with LNAPL issues in the process of RA and how it worked out. So a quick background. It's a confidential site in Gananoque, and it had historical industrial operations with a leaky fuel tank, of course. And there was LNAPL and in dissolve phase in primarily bedrock, but also in the overburden. And so there was future redevelopment planned. There was a RA and RSC process underway, and remediation was required to address the free product, right, to get this RA process going. So what was the plan? It was a staged approach. There was a source removal, decommission of the fuel tank and removal of that impacted soil. So you're just yanking the tank and cleaning up the soil nearby. There was an MPE system proposed for direct extraction of LNAPL, and I'll get into that. And then the final step was an injection, in situ injection program to address some remaining LNAPL and dissolve phase PHCs. So here's the site. It's residential, clearly, but it's an industrial, formal industrial operations nearby. And then here's the remedial area. Here is a site plan with the monitoring well network, and I'll go to some of the details here on where this plume was. So groundwater flows to the southeast. The tank was located in the building here. The green dots are no LNAPL, groundwater was clean. Yellow was no NAPL, but the groundwater was above standard. Orange was there was no product, but there was odors and groundwater above standard. And then, of course, our red is where there was product found. And so this is kind of just a general idea of this plume of the LNAPL at the site. And so our first step was the multi-phase extraction system to remove the bulk of that LNAPL. And so what that means is multi-phase extraction system, MPE, is a extraction system that splits the extracted groundwater in LNAPL and vapor into those three phases and treats them individually. I won't go into too much detail here, but basically what you have is extraction wells set up. You're pulling all the contaminant out with the three phases, and they're split up into either liquid carbon vessels for discharge to a sewer. You're splitting that product for storage and eventually disposal from the oil water separator. And then your vapor is split from the water for then treatment through vapor GAC, carbon for discharge. And so what does this look like on a site plan? The purple kind of extraction line overview is shown here, extracted some of the key wells, and we added some extraction wells as well also. And we did some overland extraction lines. We didn't have to, trench everything in. It wasn't an active site, so that saved costs. And it was quicker. And we had a pretty good containment of the LNAPL because we were hooked up to most wells that we found it in. And so what do these results look like? So here's a month by month LNAPL thickness results by individual wells. And you can see some pretty big spikes at the start here for some of the wells, but overall trending downwards after a year. Here's the average of those wells over the months. And you can see after a year, it's basically reduced from 300 millimeters on average down to below 10. But as you can see, there's diminishing returns, right? You're not getting that final no LNAPL clean result. But we saw that LNAPL area reduced by over 75%. So it was a great success. But we needed something else. We to polish this off. And so here's some borehole logs kind of just showing the different geologies here. And so we saw that pretty shallow bedrock at 2.5 meters or under 2.5 meters. And the clay had some impacts as well. You can see some notes on odor here, but the majority was in the rock, but we had to address both geologies. And so what did we do for the injection to finish this off is we did a 2-day injection in 2022. We did 5 bedrock geotap points, like I described earlier, and then we did 10 just standard overburden direct push points. These 15 points were injected to target that remaining hotspot area that I just mentioned. And here's the site plan showing the locations. And so overall, we injected over 2,200 kilograms of Boss 200 plus in 4,000 liters. So it's pretty heavy mass of amendment in a small volume. So to address that heavy mass of LNAPL that we're trying to clean up. And so what were the results? We saw in our wells LNAPL thickness decrease substantially, basically to no visible measurable thickness. After only I think a few months, 8 months, we saw success. And so this was sustained enough for the RA process to continue as there was no measurable LNAPL following our remedial program. So in summary, we had to do 3 steps here. We had to do a UST removal to get the bulk of that contaminated soil and LNAPL from the source. We then implemented an MPE system for a year to remove the remaining bulk of that LNAPL, 75%. We then did our injection approach to then address the remaining 25% that was able to be completed with an injection of the Boss 200 plus, even with some pretty high measurements of LNAPL. That PHC mass didn't saturate the Boss, and it was able to be overcome. And that was a sustained treatment approach of LNAPL, right? It's destroying the PHCs within the carbon and regenerating to last for quite a long time and be persistent across 2 geologies, which was quite difficult. So in summary, successful risk management measures for LNAPL sites start with a comprehensive CSM. And so this really gets into some of the tools that we can use to help with developing a CSM, like laser-reduced fluorescence, LIF. And a little note here I want to add, if you're going to use RPI's products, Trap and Treat, they actually provide free lab analysis of whatever contaminant you have on your site, but PHCs here, for remedial design. So it's something we use on a lot of our sites for better understanding and characterizing contamination. And then on to LNAPL destruction. So we did talk about Trap and Treat, Boss 200, overcoming mass limitations of AC sorption. And again, that degradation kinetics, can treat up to a kilogram of PHCs per kilogram of Boss or carbon per year, which is quite powerful. And then we spoke about the LNAPL immobilization. So this is block and absorb. So Portland cement and carbon combined are more effective than if we add individually, and it's proven effective at mobilizing LNAPL and sheens in situ. And then we talked about some of the injection approaches and how we can overcome some of the limitations potentially with direct push, with geotap, and getting into bedrock. And overall, there's many ways of effectively degrading or immobilizing LNAPL in situ to help the overall goal of allowing easier approvals of RAs. And that's it. I hope I interested some of you and didn't fly through it too quick, but you can open up to questions now.
All right, cool. Thank you, Eric. We do have a few questions in here. I'll lob them your way and see how they go. The first one was, this relates to, I guess, block and absorb. Why doesn't the Portland cement turn to a block in the ground? Does the addition of the AC prevent solidification?
That's a great question. So what I would say is that we manage the concentration of Portland cement to make sure it's not hitting a level that is becoming excessive. And I don't know if the carbon itself is creating an effect that, limits that effect from happening. It's more so of that you can reduce your mass of cement because you're adding carbon, which, can then immobilize more PHCs through absorption. And therefore, you don't need as much cement to immobilize through stabilization. So it's kind of just a trade-off of how much can do what. But yeah, that's a good question on if there's actually a effect within the carbon itself.
Yeah, I think you're right. I don't think there is. I think going back to the testing, like we did extensive bench scale treatability testing on that technology prior to that pilot scale test. And depending on the soil type, we found that if you limit the concentration of Portland cement to like 3 to 5% kind of thing, the soil is still workable. It doesn't turn into a mass of concrete, essentially. If you start getting above that, then you do risk that happening. But at that point, too, you're probably not cost effective if you're adding that much amendment into the ground. That's a significant amount you're adding. Okay, next question. And I just remind everybody you can put these questions in the Q&A or in the chat feature, and I'll pass them on to Eric. The next question, actually, maybe I'll answer this one, Eric, or I could actually, I'll throw it to you. You can see if you can answer it or just pass it to me. But the
Okay.
question is, can you conduct tilt monitoring after injection to see the orientation of the fractures and where the amendment went? So I think he's talking about, or this person is talking about geotap holes in particular.
We've been asked this before. Yeah, I'll let you answer this because I know you did some investigation on this, but I know we
Yeah.
talked about this in the past.
Yeah, I mean, it's a very good question because whenever you're injecting, especially a particulate amendment under high pressure into a formation, you will get some fracturing happening. I think the differentiator here is the approach of the injection that we're using. So we're not talking about widely spaced injection points where we're injecting, thousands of liters of amendment per interval and trying to propagate that out a fair distance into the formation. In that situation, yeah, you would want to know where it's going and what the orientation of the fractures are and the radius of influence. The way that we design these programs, if you go back to the slide Eric was referring to earlier, we use a fairly tight spacing and very controlled injection volumes. So on any given point, depending on the formation and the spacing, we're injecting, a few tens to maybe a couple of 100 liters per shot, as we call it. So they're not going out very far into the formation, and we're relying on the high density of those tightly spaced, tightly controlled shots to get, as uniform a distribution as we can into the formation. So in that situation, the tilt monitoring doesn't really matter because we are controlling the distribution by different means. The next question is, has this approach, I'm not sure which approach, but has this approach been used for approval of RAs in Ontario? Maybe just in general, like, well, any of the approaches, have they been approved? Have they been used for approval of assessments?
Yeah, well, with the case study we mentioned, right, was in an RA approval process, right? And then that's specifically with addressing LNAPL is a key remedial objective, right? When you're trying to do these RA applications. And so, yeah, we've done it multiple times. It's I guess the question is it more like, are these approaches approved within the process themselves in detail, or is it just these processes of work removing the LNAPL as designed, and then the RA process can continue on as planned, right? Is that kind of separate?
Yeah, that's a good answer. I think it's the RA approval process doesn't specify the method as to which you have to remove or immobilize the NAPL. It's just the end result that counts.
Hmm.
And I know in other jurisdictions, for example, we've done this even on DNAPL sites
Yeah.
where there wasn't really a requirement to um, destroy mass per se. It was to get below that threshold. If you go back to what that
Yeah, the
earlier
BC.
slide you did, yeah, where it was designated a high risk site. And that was also in support of a risk assessment approach. So there are precedents out there, and really the focus is not so much the technology, but the result of the technology that matters.
Hmm.
Another question here is, oh, this is a good one, and I don't know the answer to this one. Have you ever gone back to one of these BOSS 200 plus sites, a year or two later with the LIF to see how effective it was? Or is the effectiveness based on monitoring well sampling only?
That's a great question. So yeah, it is primarily only monitoring well sampling, right? To understand groundwater concentrations. That's kind of the measurable that we're looking to use, right? And especially with RAs or any of these remedial programs. But I'm not aware if I'm sure we've done lift on sites where we've injected, but it's probably more so to characterize perhaps areas that weren't delineated previously, right? Like, hey, there was an area of the site that actually had a spill that we didn't know about. We need lift over here. But it is a curious question to say, hey, we injected BOSS 200 plus, we're removing LNAPL in these monitoring wells. Do we do lift to see if we're connecting some dots here and fill in some gaps as
Hmm.
part of that post remedial monitoring?
Yeah, and I think it's important to note that like what the applications that we're talking about here are to satisfy that objective of um, getting rid of the NAPL or the mobility of the NAPL. And really that's based, apart from the BOSS 200 plus approach, which is a destruction technology, there's also a stabilization or a sequestration component to it. And really, you're right, Eric. I think that the measurement is, does it show up in any of the monitoring wells or not?
Mhm.
Because that's the trigger. Apart from the solubility rule in Ontario, that's the trigger you're looking for to decide whether you have that mobile or NAPL presence or not.
Mhm.
Okay, another question here is for the Packers and fractured bedrock, can you do multiple depths of injection in the same borehole, similar to injection in the overburden?
Yes, yes. So you can definitely do that. You're able to inflate and deflate the injection packers within the same hole, and then reset them at the depths that you're targeting. And so I didn't get into too much detail in the presentation on what this looks like, but a program typically you're going to have a conceptual site model, right, where you have a good understanding of contaminant depths and extent, and then you install your injection wells to hopefully target that. But you can actually use these packers to discrete sample vertical depths within the injection wells to understand vertical delineation of the contaminants within that hole, and then subsequently target them with the injection of the amendment where the massive contaminant is. We also employ borehole geophysics and coring at these sites to understand fracture networks, to understand where available fractures are for injection prior to our injection. So it's quite detailed when we're assessing bedrock injection programs. But yeah, overall, to the question of you know discrete intervals of injection, is definitely the plan for these types of injections.
Yeah. Okay, I have another question here. Are there any daughter products as a result of using BOSS 200 plus, or are there any unwanted secondary parameters?
It's a great question. Um, so no, but there are so the end products are non-toxic byproducts of the end degradation, right? So it's like water and carbon dioxide, and that's of course not a concern. But I would mention that some of the TAs that we add or nutrients can be adjusted based on the jurisdiction that we're working in. And so, for instance, nitrate is used as a a TA to help with anaerobic bio. But say you're near somewhere that is a concern, a COC, and we can remove that and use different amendments. Similarly with sulfate or what have you, right? So it's not necessarily an end product that's a concern. There's not like a generation of something hazardous, but it's more so the actual amendment itself can be adjusted to make sure that there's not some COC that we're adding to the system.
Right. So yeah, so you're saying like if we're in a potable groundwater situation that has a target for nitrate, that's
Yeah.
something we wouldn't want to be contributing to.
Yeah, it's primarily nitrate. Like sulfate is a part of it as well, but that's more of an aesthetic
Yeah.
issue in that scenario. But
Yeah.
and I don't think we ever actually would hit that level with the amount of sulfate that we're adding.
Mhm. Yeah, and there are intermediary products, breakdown products, but because we're degrading hydrocarbons, unlike chlorinated solvents, where some of
Yeah.
those daughter products are actually regulated as well, and in fact more toxic, the degradation products of the hydrocarbons are typically they're non-toxic or not even regulated. That I think is all the questions. If there's any other questions, you can pop them in the chat or the Q&A now, and we can get to them. Eric, if you want to
Yes.
stop sharing, actually, maybe I can just take it over. Okay. So, thank you. So we do have some other talks coming up. It's actually a busy fall, as you probably know. Fall is conference season. So we have people across the country presenting at different conferences. If you're interested in details on any of these, there was a newsletter that went out yesterday from us that details them all and provides links. If you're missing that, or if you want to get registered, please let me know, and I will pass that along to you. And also, don't forget the biggest event, in my opinion, of the year are the smart remediation conferences. So we've always done Toronto and Ottawa, but we haven't been back to the West since the BC before COVID. But we are coming back in the spring, or sorry, in the winter. So registration is open for those events now. If you go to the smartremediation.com website, you can sign up for those. And as of that, I would say we still have a few minutes left. We can stay on here if there are other questions. I think someone did have a question. Gail, if you want to type it into the chat, we can answer it. But I will say thank you once again, everybody, for joining us this afternoon. I hope you enjoyed the talk. Feel free to reach out to Eric or I with any questions. If you have any sites in particular you'd like us to look at, or more detailed information on any of these technologies, we'd be happy to speak to you about it. If there is nothing else, which looks like there are not, again, thank you, and hope you enjoy the rest of your afternoon.
Perfect.
Bye.
Thank you, everyone.